record. All right, we still have another 20 seconds to talk about the election. How's everybody doing? I think that kind of sums it up, Hannah. That's great. All right, it's 10 o'clock. Let's go. Let's stay focused on the class. First of all, I want to say thank you to everyone for filling out the poll, the survey, and mid-course evaluations. That was very helpful. And I do note that the most interesting to me was the distribution of how are you feeling was very uniform, meaning that I was hoping people were feeling a little more better and a little more optimistic and positive, but it was a very uniform distribution. In other words, some people are feeling really bad, some people are good, but it's really kind of evenly distributed. So I realize that it's a difficult semester and that there's a lot of stress going on, and certainly compounded by, you know, the election and the virus. So we're doing our best, everyone, but there was a lot of positive notes about the class itself, and I want to thank you for that feedback, and also acknowledge the GSIs and the TAs who have been doing a really great job, and that was widely recognized. So thank you for that feedback. We're going to go through it even in more detail and take notes of all your points and suggestions in the next couple of days. So now we're going to switch gears into something, one of the other topics that I find very fun in this class, which is we're going to develop a formal logic that's different than propositional logic or predicate logic, but it's specifically for working with databases. And it has only one operator. Well, I guess you could say it has negation and it inherits some of those elements, but it has a new operator that we'll introduce right now. And the material is in the two texts that we're using, the Sumathi online text, it's in 6.5 and 6.7, and the Al-Masri text, it's in chapters 14 and 15. So what we're going to do is develop this formal logic, and in this case, you just bear with me because it's a little different than the other formal logic. Here, the logical variables are going to be sets of attributes. So what do I mean by that? I'll make that clear in a minute. And the operator is going to look like an arrow. It's going to look like the implies operator, but it looks different in this context. So that the resemblance is only coincidental. And just like in logic, we do look at conditions under which the operator holds true or false. So let's jump into defining that, and then this will be more clear. So the concept is something called functional dependency. Functional dependency, and let's consider we have a relation with, let's say, 3 different sets of attributes, X, Y, and Z. So remember, I can group these in some way. So, but let's say we had something like a relation with name, birth date, and age. Okay, and here we might just say that this is the key for that relation. All right, that's what I'm saying. There you have. Well, we might have lots more attributes, but we're going to group them into three types here. And what we're going to do is say that we have there's a functional dependency holds that this is true, that X determines Y, one set of attributes determines another set of attributes. And we say that as X determines Y, or Y is functionally dependent on X. Okay, this is just the way you say it. And the condition is that when this occurs, when for all rows here, all rows, or any pair, sorry, for all pairs of rows, if the values on the pair of rows match on the X attributes, then they always will match on the Y attributes. So in words, this means whenever you have 2 rows that agree on X, they will also agree on Y. All right. Now let's look at an example here. We have this table here. We have three attributes, A, B, and C. Now, and my question is, could A determine B? All right. So what does that mean? For A to determine B, right here, for A to determine B, it has to be the case that whenever something matches on A, so that means do we have a row where two things match, right? That's the case where we have a row, two tuples. This is tuple, let's call it I, and this is tuple J, okay? And they match on the X value. So in this case, I have Ti, or let's call it T1. Let's call it T1 and T2. Actually call it T1. No, let's even be smarter about it. Let's call it, this is actually tuple, we'll call that tuple 2, and this is 3, 4. This is tuple 4. So T4, okay. T2 on A is equal to T4 on A, okay? And now we want to know if A is going to determine B, then that would have to be the case that T2 of B equals T4 of B, right? And it does. So the answer is here is yes. Okay? Let's try another one. And just to get this idea a little better down, how about between B and C? Does B determine C? So again, in this case, what we'd be looking for is where do we see tuples match in the B column? Anybody want to, do you see that where they match? It turns out to be, they match on this one, and this one. So the question is, do they always match on C for those? Or sorry, this one, and this one, right? I have, they all match here. So in all those cases, they'd also have to match on the C. Do they?
No.
No, they do not, because this guy violates. Okay, so the answer is no. Okay, it does not determine, does not functionally determine that C. Now, how about C determine A? Let me get rid of all this, and you guys tell me. Does C determine A? Anyone want to venture to making a guess on that? Does C determine A?
No, because
okay, good. Why?
Well, just because on, I think it was 2 that didn't match up. So like 2, 3, and then 2, 2. So like A, it doesn't match on A.
No, remember, but here, the C determine A. So here's a case where they match on this case, right? But they don't match here. All right? That's what you're saying? Exactly. Okay, good. Does everybody get that? What we're doing? It's fairly easy to check once you get the idea of what we're looking for, but I just want to make sure you understand it. So it's where it has to hold on all the cases where you match on a row. You also have to match on the other on the other row. Okay. And it's, why do we call this functional dependency? Okay, so now we're going to go back to that thing we talked about a while ago, which was about the difference between a relation and a function. Remember that? So this is actually, this is really about functions here. Look at these, right? These are functions. And the key thing is that it has the vertical line only can touch the graph once. Okay, so that means that for every x, there exists only one y. Okay, for every x value, there exists only one y. That's a property of a function. But a relation don't have that issue. And here, right, you can have more than one. Okay, you can have, it's a generalization. So here's a case where you have values of x. So I'll write it out here. For some x there is more than one different y value. Okay. All right, and remember, that's a big point in this class because this whole class is about relational databases, and so this business is important. And this is the category of mathematical objects that we use to model the database mathematically, and it's a foundation for relational algebra. Now, if you look at this again, functions here have a special property. They're like relations. They're a subset, in fact, but they happen to be where there is no x that violates that has more than one y value. Okay, so it's a special case of relation, and that's exactly what we're getting at here. This is saying a functional dependency means that basically for every x, there's always one y. There can be not multiple y's. Okay. So that's what we're getting at. And you can basically do this. Now you have basically a function, sorry, a relation is a multidimensional function or multidimensional object, right? And each of these attributes are dimensions. Right. Now, maybe if that's confusing to you, don't worry about it. But basically, I'm trying to make an analogy for you that why we create this whole thing is it turns out, and you're going to see how it turns out to be extremely useful for reasoning about databases. But we have to make this distinction crystal clear between functions and relations. And that's what we're doing with functional dependency. All right, so look at this one here. I have name and birth date. And do you see that now that birth date will determine age? So does anybody want to explain that to me? Why, do you agree with it? What is it saying?
Anyone with the same, or everybody with the same birth date is going to be the same age.
Exactly. Thank you, Justin. That's exactly right. So we can have many people with different birth dates. That's fine. That doesn't matter. But if I have two people with the same birth date, they better be the same age. So that's a functional dependency there. How about what if I wrote name determines age? Would that be true? No, right? Because I have two people with different names. I could have two people with the same name, but would have different ages. Okay, so that's not a functional dependency. Okay, so we're gonna talk about that in 1 second. I also want to say that this is important, notational convenience here. Sometimes, because as I mentioned, we're gonna have multiple attributes on one side or the other of this arrow, the determine functional dependency arrow. Then, so sometimes I will write them as in terms of parentheses, or sorry, what are those called? Brackets, curly braces. Then sometimes I'll leave off the curly braces, and sometimes I'll leave off the commas. Okay, and I just want you to know that that's just for convenience. There's nothing that you can just sort of think of those being combined together. And remember, this kind of came up a little bit when we talked about multiple attributes being part of a primary key, called it a composite primary key. That's where you essentially take those two attributes and glue them together, and then that whole thing you can treat it as one composite key. And that's basically what we're doing here. All right, so we can do that. All right, so now let's go to what we call functional independency. All right, now here, this I don't like this symbol the way it came out, but it's basically the arrow but with a slash through it. Okay, and what that says is that there only has to exist a case where they match on X, but they don't match on Y. Okay, they don't match on Y. And remember, it's very much like what we do with in logic. Remember, where we're trying to prove something in a truth table, all we need is one counterexample, and the truth table and the assertion doesn't hold, right? So it's a little like entailment here, right? Remember when you had this, you had to have this case. Anyway, I'm probably confusing you. Let me leave this off. But basically, this is just a counterexample. There exists a pair of rows where they match on X, but they don't match on Y. So the perfect example we came up with, actually, let's not use that one, but like name does not determine birth date. Okay. All right. So now we can start talking about the functional dependency in terms of it will change depending as the data changes. This is very important. So it's not something you can say is true of the whole database, or you can make an assertion or a constraint to that effect. But it's gonna change. And what you do want to do is this idea is you can prove it by looking at an instance of the data. Remember the state, which is R of R, right? That's the state of the database, and that's always a subset of the possible rows that is active, that's being used at any given time. All right. And now we're going to look at something where we're going to start to be able to use the equivalent of inference rules, but for this new logic that we're just defining. So let's imagine that we have a set of functional dependencies. Okay. Remember, each functional dependency has the form X determines Y, and maybe Y determines Z, right? These are the functional dependencies. And so F is a set of these guys. And now we can use this. We can put our entailments to use here. And we're going to say that F, a set of functional dependencies, can determine a new functional dependency if I can go through a process of deriving it from inference rules. So the thing on the left, we call the left-hand side is the assumption, and the thing on the right is the right-hand side is the conclusion. So that's this. So now let me start to introduce the inference rules to you. So the first inference rule here is that if you have this, X determines Y, then you can conclude that, X determines Y, then you can conclude that X determines Y. Now that's sort of obvious, but we need to assert it because we're going to use it in various proofs. But it basically shows that if you have, let's say, a copy, you have the student ID, last name, that you can then conclude that student ID determines last name. Oh, wait, that's wrong. Student ID determines last name. All right. Okay. Now, by the way, does student ID determine last name? Anyone?
Maybe not.
Why?
Well, I guess I'm just thinking that there's a lot of different last names. But I guess that but the student ID is unique though. So
yeah, exactly. So that's right. So you're good to raise this question. So there are a lot of last names, right? But the student ID should be, if you match on the student ID, you should match on the last name, right?
Yeah. So I guess it is true, but yeah, that's interesting.
Yeah. Now, last name, how about this one? Last name, where's my pen here? Let me just ask you guys, last name determines student ID? Anyone else?
No.
No, very good. No way. Okay, good, because that's exactly right. So you're getting the idea. Last name does not determine student ID because there could be many people with the last name, as there are in this class, and they have different IDs. Okay, good. Now let's go on to the next inference rule, IR0. And here we have a relation with a set of attributes X and another attribute A. Okay, so that's what I try to do by underlining this to indicate it's a vector X. It's a set. Well, actually, why don't we even call it going to call it, using the term loosely, let's call it a list of attributes X. And now if X is a candidate key, okay. Oh, I should say, actually, sorry, this is that was actually not what I meant to say. This is, let me take this out. What I'm doing by the underline here is that X is a candidate key. By underlining it, just like we are with the primary key. Already that X is a vector and A could be a vector. If X is a candidate key for the relation Rxa, and A sub I is a subset of A, then we can conclude that X determines that subset. So each candidate key determines all the other attributes. All right, so let's actually prove that. And so I'm gonna show you how we prove these kind of properties. And the proof is that we assume otherwise. We're going to go toward a contradiction. So we're going to assume otherwise that X, first the thing on the left, that X determines A, or X does not determine A sub I, then there exists a pair T1, T2, such that T1 of X equals T2 of X, and T1 of A sub I does not equal T2 of A sub I, right? That is a condition for this to, this here is a condition for this, right? I just wrote that right above for a functional independency. So I'm assuming it's independent, and then I want to ask if, and then this would have to hold. And now here's I want to claim that we are immediately at a contradiction. Anybody want to point out why we've hit a contradiction right away? What's contradictory about this statement? I'll give you a hint. It has to do with it being that X is a candidate key. Anyone? Okay, the answer is right here. This right here is a contradiction. If X is a candidate key, there cannot be two rows with the same value, because a candidate key by definition means that all rows are unique. So this is a contradiction because if X is a CK, then each row is unique. So the very first part of it can't happen. Okay? Do you see that? And that means that we've reached a conclusion. So therefore, X must determine A sub I. All right. Good. So that's actually an interesting property, right? That means that if you have any candidate key, that's going to determine all the other attributes. Because the candidate key is unique for each row. So by definition, by construction, essentially, it's has a functional dependency. It functionally determines all the other attributes in the relation. So candidate keys are quite powerful, and that's why we spend time distinguishing them. Remember, there are minimal super keys. Okay. All right, now we'll go to Armstrong's 3 inference rules. Here, these are the next 3 have this nice name by a researcher named Armstrong, who defined them in 1974. And the first one is called reflexivity of subsets. All right, what does that mean? So this is IEOR1. If you have if Y is a subset of X, then it must be that X determines Y. So X determines all of its subsets. All right, does that make sense? So if I had something like, let's call it birth date and major, this will determine major. Does that make sense? Everyone? Okay, what is it saying? Well, it's saying that on the left-hand side, you have to have birth date and major, 2 rows where those happen to match. And there's probably a few cases of that in every major, where I have someone who matches on both birth date and major, right? But if they match on that, then they're also going to match on major. Do you see why? All right. So that's not saying anything very profound. It's pretty obvious once you think about it. But that's just it's important to have that inference rule, and we can prove it. Let's do that. So again, we're going to assume otherwise. Assume otherwise. So we have Y is a subset of X, and X does not determine Y. So that means that there exists T1, T2, T1 of X equals T2 of X, and T1 of Y not equals T2 of Y. But this is a contradiction because Y is a subset of X. You can't, if they match on X, they have to match on Y. Right? So Y is a subset, right? So that is a contradiction. So therefore, X determines Y. Good. Now let's go on to, here's another example, right? If you have last name, first name, that's going to determine the first name. Good. Strengthening the assumption. This proof is a little longer, so you're going to need some room for that. And this is, strengthening the assumption is where you have, this should be written as this, X determines Y, and that should not be there. Okay, I'm sorry about that. Came out badly. Okay, so it's like that. So if you have X determines Y, then you can add something to the left-hand side. That means you can add another attribute to the left-hand side, like Z, and it's still going to determine Y. Okay, there's no harm. Okay, and then also there's a slightly stronger version of this. I can add something to both sides of the arrow, and it will still be true. So you can augment the a functional dependency by adding something onto both sides. Right now, I'm going to prove it for you, but before I do, Malik has a question about is the candidate key the same thing as a primary key in application? And the answer is yes. In fact, the thing is that you may have multiple candidate keys, and there is and then you have a choice of choosing one as the primary key. But all the candidate keys have the property of being minimal superkeys, meaning that you can't take anything out of them and that they're unique in that for that set of columns, set of attributes. There's no duplicates. Okay, good. So now let's prove this thing. And again, we're going to assume otherwise, as we have been doing. Assume otherwise. So now we have that x determines y, and x xz does not determine yz. So I'm going to prove this one. Okay, and now that means then, because of this, I have for all t1, t2, if t1 of x equals t2 of x, then t1 of y will equal t2 of y. And we'll number these, 1, 2. Okay, that's just repeating. Everybody see that? That's just basically repeating that first condition. We also have the second condition here, and that means that there exists T3 and T4, we'll call them, where T3, let me be very clear and not sloppy here, T3 of xz equals T4 of xz, and T3 of xy does not equal T4 of xy. Okay, I haven't done anything but just write down the conditions of this right here. Okay, that's what I've assumed. Now let's look at it a little more closely. I'm going to say from, yes?
Is it supposed to be XY or YZ for like T4?
Yes, thank you. Wait, you're right. XZ, YZ, thank you. Thank you, very good. Thanks for catching that, Jason. All right, now from IR, now we're going to take this one, the third one here, and apply IR1 to it. So what does that mean? We're going to be able to say that this is true by the subsets, basically. Okay, that if this is true for all T1, basically this, right? If you determine all this, then T3 of x equals T4 of x. You see that? Basically, that it's a subset. X is a subset of xz. So T3, they have to match on T3 and T4. And similarly, from 5, this one here, 1 and 2, okay, here they match on x, right here, and they have to match, if they match on x, then they have to match on y. So T3 on y has to equal T4 on y. Okay, so I've taken these first two, T3 and T4 just happens to be one particular instance, and this is for any pair. Sorry, over here it says for any pair, if they match on x, then they must match on y. So if they match on x here, they have to match on y there. Okay, and then from 3, it's also true that T3 of z matches T4 of z, 7. And then that's just the same thing, the same reasoning. I can put IR1, right? It's a subset of 3. And now we're going to combine 6 and 7 together. what do I got here? 6 and 7, they match on Y and they match on Z. So therefore, T3 of YZ equals T4 of YZ. Call that 8. And this contradicts four. So that breaks that. Therefore, XZ determines YZ. Okay. And this is similar reasoning. X determines Y. If you have X determines Y, then that entails that XZ determines Y. You can put something else. You can put something just on the left side without putting it on the right side. So here's the example here. If I have student ID determines first name, I can say student ID and last name determines first name and last name. So I've just appended, I've augmented the left and right side with a new attribute. And I'm free to do that, and it will always be true. Make sense? Okay. Let's go on. Let's do transitive. Here, this came out wrong as well. This is
Yes,
X determines Y. Yes.
So in the previous proof, how did you start with the assumption? Is that something just came up, or like, was there a reason for that assume otherwise statement at the start?
Yeah, let's go over it. Why do I do this? Assume otherwise? That's what, it's a very effective proof technique in general, is that you just take the starting point, which is the left-hand side of the assertion, and then I assume that it's not true. Okay, so then I take the left-hand side, and then I flip the right-hand side and make it negative, make it false.
I see.
And then I basically try to work through that to reach a contradiction. And if I can reach a contradiction, then it has to be true.
Got it. Thank you.
Sure. Okay. So we're gonna get another chance of doing that right now. Here we'll do a slight variant. So I'm just gonna cross this off. That came out a little bit weird in the typesetting. So we have transitive says that if I have an attribute X that determines an attribute Y, and Y determines Z, then I can conclude that X determines Z. So that is a lot like a transitive law. If X equals Y and Y equals Z, then X equals Z. Right? So we're showing that that property holds for this functional dependency, and let's prove it. So we're going to assume the left side. So X determines Y, and Y determines Z. That means that for all T1 and T2, when T1 of X equals T2 of X, then T1 of Y will equal T2 of Y, and when T1 of Y equals T2 of Y, then T1 of Z equals T2 of Z. Therefore, X determines Z. All right, now that is just basically grows out of the transitivity of equality. So, right, if they match on the X, then they're going to match on the Y. If they match on the Y, then they're going to match on the Z. So it's just a chain that gets you right to the Z value. So that's why you can use that chain in functional dependencies. Okay, so here's an example of this. If I have professor ID determines department, and the department determines department manager, then the professor ID is going to determine the department manager. Make sense? Good. Okay, so that's helpful. Now we can put together chains
Professor?
of functional dependencies. Yes.
If you scroll up a bit,
Hmm.
in the SIDL name,
Here?
yeah, the by similar reasoning part right on this page, it should be XZ implies YZ, right?
Yeah, well, remember this here is actually, remember, like, there's two different versions. There's this version and there's this version.
Oh, okay.
Yeah, but they're very close. Okay.
Oh, okay.
So I didn't
Makes
mean to
sense.
confuse you there. This is it. What I did here was I added this is like the Z, I added on both sides.
I see. Okay.
Okay, good. All right. Everybody get the transitive right there. Good. Let's go on to the more rules. So it turns out that these are derivable using rules 1 to 3. So but they can be helpful. So here's one. X determines YZ. If I have that, I can conclude that X determines Y. So that means that essentially, if I look at it, you can remove things from the right-hand side. You can remove, in this case, Z from the right-hand side of a functional dependency. So let's prove that. So this also has a name. You're think of this as, remember, there's the assumptions and the conclusions. And by removing something, you're weakening the conclusion. Does that make sense? Weakening the conclusion. So the proof here is that you have X, sorry. We know that proof is that Y, Z, we know that that determines Y, right? That's just from the IEOR1, right? An attribute, set of attributes determines all of its subsets. And then we know that X, we can conclude that X determines Y using what? Let's call this, we'll call this 1. So we're going to use, well, X determines YZ plus 1 plus IR3, the transitive. Because what we're doing here is that X determines YZ, that's from up here. I've just shown that YZ here determines Y. So if I put those together at the chain, then I get that X determines Y. Okay, so that comes around very easily if I have IR3 to apply. All right, so the nice thing is here, the note here is that you can use IR4 to decompose a wide functional dependency into narrow functional dependencies. So if you had something like X determines A1, A2, A3, AN, then I can conclude the following, that X determines A1, X determines A2, X, whoops, X determines A3, X determines AN. Okay, so I have this one functional dependency here. Let me slide up for you. This one functional dependency here is going to determine a whole bunch of functional dependencies over here. Right? So that's why we call it decomposition. And here's an example. So if I have student ID determining last name and major, then I can break that up into student ID determines major, and I can say student ID determines last name. All right, and that makes sense too. So it's sort of in some sense like the opposite of the augmentation rule that was earlier, the IR2, because IR2 lets you add stuff on, and decomposition lets you break things down. Okay. Now, do we have time for union? Yeah, let's do union real quick. Union is basically saying that I have X determines Y, and X determines Z, and then I can do this, X determines YZ. So this is a little bit not obvious, at least to me, so let me prove it for you. Let's call that FD1 and this FD2. So the proof is, first of all, I know that XX determines ZX, and that's the FD2 and IR2. Okay, so I basically just supplemented both sides of FD2 is over here, X determines Z. I added an, oh, whoa, wait, sorry, that was not kosher. It's XX determines ZX here. So I just added an X on both sides of that. And now I can use my, this nice function here, X determines ZX, and that's from IR00, right? And then next I can say that XZ determines X, I'm sorry. I'm done because XZ determines YZ, and why is that? Anyone? Well, I'm going to start with X functional dependency 1 up there. X determines Y. So, and IR2, wait, XZ, determines YZ. So I got FD1 and IR2, okay? So I'm doing the same thing. I'm augmenting the first one with Z on both sides. That's fine to do as well. And then I'm going to claim that X now determines YZ. And that is, I'm combining, let's number these, 1, 2, 3, 4. This is a result of 2, 3, and IR3. So I'm taking 2, X determines ZX, and ZX determines YZ, so therefore X determines YZ. That's union. And so here we also note that we can use this one to union together many of the small, narrow functional dependencies into one wide functional dependency like this. And here's this should be in here like this. This is just X determines A sub n. Okay, so if you happen to have a lot of little ones with there's only one thing on the right-hand side, then you can combine them up together into one wide functional dependency. All right. All right. Now, just I'm gonna there's a way to wait a second. Why do I have that? Oh, forget about this homework. Sorry, that was a little bit of an artifact in there. All right, now there's another one called pseudo-transitive. We're going to wait until next week to go into that. But you have some of the beginnings of this. Now we'll be going over more of it next week, and so I would say you can hold off on starting on the homework. It's not going to be due for a little bit longer, so basically get a week off of doing homework. And then we do have a lab on Friday. So I hope to see you there. And I hope you have a good weekend, everybody. Thanks for being here. And let's see let me go back to checking out this election. Uh-huh. Very interesting. Biden has squeaked through on Wisconsin.